So the last part of chapter 10 is concerned with the solid state of matter, and we're going to begin by just doing a brief overview of different types of solids. So in a crystalline solid, the atoms are organized in an orderly array called a crystal lattice, and metallic elements tend to form crystalline solids. And so what we will see in a metallic element is a regular repeating three-dimensional array of the metal atoms building up the crystal lattice. Molecular substances can also be crystalline solids, but in this case what's happening is that the repeating particle in our orderly crystal is a molecule. And a good example of a crystalline molecular solid would be something like ice. Now, when we look at ionic compounds also form crystalline solids. But in this case, the particle that is repeating to build up the crystal lattice are positive and negative ions. And as we learn later on, what's going to occur is that these ions will organize themselves to minimize the distance between oppositely charged ions, which will attract, and to maximize the distance between ions with the same charge, which repel. And in this way we end up with a material where the attractions are always greater than the repulsions and the whole thing holds together. Some compounds and non-metal elements form what are referred to as covalent network solids. These are crystalline solids, but rather than there being like a regular repeating pattern of atoms or molecules that are like not in any way connected to one another or ions, what we have now is a network of non-metal atoms bound together by this extended array of covalent bonds. So classic examples of this are silica or quartz, where we have silicon atoms, each of which is bonded to a tetrahedral of oxygen atoms, but then each oxygen atom is actually bound to two silicon atoms. And in this way we end up with a crystalline material where we have a network of covalent bonds that extends throughout the whole structure. Another example of a covalent network solid is a diamond. And in diamond what we have is we have sp3 hybridized carbon atoms that are tetrahedrally coordinated or bound via covalent bonds to four other carbon atoms. And every carbon atom is connected in a tetrahedral fashion to four others. And that creates a very rigid, very hard structure. And diamond is the hardest known structure with a hardness of 10 on the Mohs hardness scale. And you can kind of understand why this is the case. It's because, there's these very strong covalent bonds that are linked in a network throughout the whole thing. Another allotrope of carbon is graphite. Graphite is slightly different. In graphite, the carbon atoms are sp2 hybridized, and they are connected to three other carbon atoms in a trigonal planar fashion. This kind of leads to sheets that have these sort of hexagons of carbon atoms. And what we find is that we get these sheets, and then between these sheets there are only these sort of like weak dispersion forces. So one layer of the graphite can easily slide past another layer of graphite because it only requires breaking these dispersion forces. So graphite is quite slippery and is often used as a lubricant because of these weak connections between the layers allow the layers to slide. So the other thing about graphite is because these layers are only held together by weak dispersion forces, when you drag a piece of graphite across a piece of paper, you can pull off a single layer here because the dispersion forces with the paper will exceed the strength of the dispersion forces between the layers. So graphite's kind of an interesting one. There are some other compounds. Silicon carbide also has a structure that is very similar to quartz that form these covalent network solids. So at this point we've got several different types of crystalline materials that we've looked at. We've got metallic crystals, we've got molecular crystals, and then we've got these things that we're calling covalent network solids. Okay. We also have ionic solids or crystals. So you should be able to kind of classify crystalline material as falling into one of these four categories. It's not too difficult. Obviously, the repeating particle in a metallic crystalline material is going to be a metal atom. The repeating particle in an ionic crystalline material will be alternating positive and negative ions. For a molecular crystalline material, the repeating particle will be a repeating molecule. It's at different positions building up the crystal lattice. For a covalent network solid, it's going to be non-metal atoms, but they're going to be bound in this network of covalent bonds. It's a little harder, it's a little more difficult to recognize this. Covalent network solids tend to have very high melting points compared to molecular solids. You can remember and they tend to be a lot harder than molecular solids, so very, very tough. And you can remember that quartz is an example of a covalent network solid, diamond is an example, and that graphite is an example. You can just memorize a few of them. Ionic solids are high melting points, very, very high melting points, as are metallic solids. So you should be able to recognize and categorize a crystalline material into one of these categories. Now, not all solids are crystalline. Some are what we call amorphous. And in amorphous solids, the atoms are arranged in a disorderly or random fashion. Perhaps one of the more famous examples is amorphous silica of the type that's found in glass. And really what's happened here is that there's been sort of, insufficient, by the time that the material has solidified, the particles haven't been able to organize themselves in an orderly fashion. Many very large molecules like fat molecules and oil molecules or lipids often form like waxes, which is another example of an amorphous solid. So amorphous solids are often formed by very big molecules that have difficulty in getting themselves organized into a regular repeating pattern before they become solid. Now, one of the properties of crystalline metallic elements is that they are quite soft and malleable. And it's sort of, when we think about this at an atomic level, it becomes evident as to why that might be. So a metal can be thought of as being composed of a regular repeating pattern of spherical metal atoms. And, when you think about this, it's like a big old pile of ball bearings, and if you put a little pressure on this, these layers can move past one another without actually breaking any bonds. The bonds that get broken are exactly the same as the bonds that get formed, and as a result, because we have this sort of slipperiness between the layers of the atoms, it's pretty easy to bend and stretch a metal without breaking bonding and having it snap. Now, about 5,500 years ago, we figured out that if you add a little bit of tin to copper, you can produce a metal called bronze that is a lot tougher than either tin or copper by itself. And this was like really important because now we could start doing things like building cannons and all sorts of and metalworking tools that were very hard, picks and things like that were a lot tougher than copper. And so what's happening in this alloy of bronze is kind of interesting. So bronze is an example of an alloy, and you get an alloy when you have a host metal, and then you combine that with one or more other sort of elements that are sort of like non-host elements. And what you end up with is something that's very different from the host and often very different from the elements that are being added. Bronze is an example of a particular kind of alloy called a homogeneous alloy. And in a homogeneous alloy, what's happening is that the atom that you're adding, tin in this case, is evenly but randomly distributed amongst the host. So typically how this is done is that you'll bring both of the metals into the liquid state by adding heat, stir them very thoroughly, and then allow it to recrystallize. There are what we refer to as heterogeneous alloys, where you have small islands of another element like dispersed throughout the alloy. And galvanized steel, you might have seen that, where you can see like different kind of like crystals forming in here, and it's kind of more like a conglomerate. That's a good example of a heterogeneous alloy. Galvanized steel is often used where you want to have a material that's very resistant to rusting. They incorporate zinc into the steel, and that really helps. So alloys can also, as well as being classified as heterogeneous or homogeneous, may also be classified as what we call substitutional. So what happens in a substitutional alloy is you replace one of your host atoms with another kind of atom. And in the case of bronze, what we're doing here is we're replacing copper atoms with the slightly larger tin atom. Now, there is a rule for when it is possible to do this, and the atom that is substituting for the host in the crystal has to be within about 15% of the radii of the host, or otherwise is going to cause these layers to separate from one another, and that's just not going to be energetically favorable. So it has to be of similar size to the host, whatever you are substituting. So tin's a little bit bigger than copper, and it turns out that you can put up to about 30% tin into copper without too much fuss. So why does adding the tin make the copper or make the bronze so much harder than pure copper? What's going on there? So what happens is the slightly larger tin atoms, they result in sort of these little bumps in the layer here. This tin atom sits a little higher, and in order for that top layer to slide past, it actually has to raise the entire layer, and you can see that that's going to cause a lot of these connections between the atoms to have to be broken in order for them to get past this bigger tin atom. So it's kind of like an atomic scale speed bump, right? So as a result, the copper is much more resistant, or the bronze is much more resistant to bending and stretching than what 100% copper is. Yeah, so it's pretty cool. Now, we of course found that out by accident, right? Now, another important class of alloys, not the substitutional alloys, but what we call interstitial alloys. And interstitial alloys are a little bit different. In an interstitial alloy, what's happening is that we're going to put another kind of atom in holes, and you can see where these gaps are in here, in gaps in the crystal of the host, okay? So that's what we call an interstitial alloy. And so these gaps are often referred to holes in the host metals lattice. And we're going to learn about different types of holes later on. We're going to learn about holes that are called octahedral holes, which are actually these ones that I've highlighted here. We're going to learn about tetrahedral holes, which I haven't drawn on the screen anywhere. And we're going to learn about cubic holes, which is the hole that I highlighted on the simple cubic unit cell there.